Number 22. A cave rescue team lifts an injured spelunker directly upward and out of a sinkhole by means of a motor-driven cable. The lift is performed in 3 stages, each requiring a vertical distance of 10 meters. A. The initially stationary spelunker is accelerated to a speed of 5 meters per second. B. He is then lifted at the constant speed of 5 meters per second. And C. Finally, he is decelerated to 0 speed. How much work is done on the 80 kilograms rescuee by the force lifting him during each stage? So let's suppose this is the guy over here, or girl, I don't know. And we have a lifting cable, so we have 3 different stages. So the first stage is 10 meters long, and we just accelerate and pull it 10 meters. The second one is also 10 meters, and the third one is also 10 meters. So in this stage we increase its speed. In the second stage the speed is constant, and in the third stage the speed decreases. So this is a pretty simple problem to solve. We have to find the work. So the only equation that we are going to use is that the work is equal to the change in the kinetic energy. But in this case we have 2 different works. We have the work from the cable, that's what we want to know, and the work from the gravitational force, and this is equal to the change in the kinetic energy. So let's suppose that upward it's positive. So what happens when we do that is that the work done by the gravity, now it's negative, because let's see, the work done by any work actually is equal to the force, the dot product between the force and the distance. And since the gravitational force points downwards, so the gravitational force points downwards when the movement is upwards, this will give us a negative value. So the work done by gravity would be minus, the force of gravity is m times g, and let's say that it's a generic value d over here. It could be x if you want. Okay, so now our equation becomes the work done by the cord minus mg d, which is equal to delta k. Okay, so let's isolate the work from the cord. That's what we want. Remember that the delta kinetic energy is equal to the final kinetic energy minus the initial kinetic energy plus mgd. So we are going to apply this equation to each stage. That's what we are going with. Okay, so letter A. Let's see, the work done by the cord is equal to the final kinetic energy. Let's remember that the kinetic energy is mv squared over 2 minus the initial kinetic energy is 0 because it is stationary, plus mgd. So we just have to replace the letters by the numbers, and then we have 80 times 5 squared over 2 plus 80 times 9.8 times 10. And this gives us roughly 88.84 times 10 to the third joules. Okay, so that's the answer of letter A. For letter B, we're going to apply exactly the same equation, this equation over here. So the work done by the cord would be equal, so the initial kinetic energy and the final one, it's the same because the speed is constant. So this term, we can cross out this term over here. So it'd be just equal to mgd, because the final speed and the initial speed is exactly the same for that stage. So this is equal to 80 times 9.8 times 10, and this will gives us 7.84 times 10 to the third joules. So that's the answer of letter B. For letter C, again, we're going to use the same equation, But in this case, the final kinetic energy is 0 because it stops at the end of the movement. The initial kinetic energy is m, v squared over 2, as always, plus mgd. So let's just replace the letters by the numbers. This will be equal to minus 80 times 5 squared over 2 plus 80 times 9.8 times 10, and this will give us, let's see, this will gives us 6.84 times 10 to the third joules. So that's the answer of letter A, letter B, and letter C.